Hello? Mute your mic for a second. Okay. Hey, good morning, everybody. We're just making sure that all our technology is up and running. Welcome, and I have disabled the chat board right now, so anything that you type into the chat window is going to end up just coming to the moderators only, and it will not be visible in the room for the rest of the folks to see. So we will turn that chat permission back on when we get to Q&A, so you can pre-type your questions in the chat and don't hit enter. You can hang on to those, and when it's time for Q&A, we can get to them. So welcome, and I'll turn it back over to Maria.
All right. So you've probably all read about Stuart McClung, and he is here today to speak to you about the NASA Orion program. He is an engineer and works on lots of different aspects of Orion, and we're excited to welcome him today. So here you go.
Hey, good morning, everybody. Let me get settled in here. Everybody hearing me okay? Just do a quick sound check.
Can you give us a green check if you can hear?
We're good to go? All right.
Yeah.
All right. So just real brief about me, and then we'll get going. I've been working at NASA since 1989. Grew up back in Indiana. Actually spent a few years out in California working on the B1 program, so I really appreciate all you guys that on the West Coast that got up early, because that's early. Although you missed traffic if you had to commute in somewhere, so that's a benefit. I work with the engineering team on Orion. I worked on the space shuttle program for a long time, made a number of trips to Russia, worked with our Russian partners when I was working in shuttle. My world, when I'm not doing outreach, is power techniques, mechanisms, landing systems, primarily. That's a lot of my background. So I'm a gearhead, as people like to joke, right? I'm not the really brilliant avionics or software guy. But so I work with a variety of teams, building up hardware, getting us ready to fly. I just got back from 9 months in Florida, where I was working with our production team down there. And if you saw our Facebook and our other posts last week, we rolled the vehicle out, the EFT-1 vehicle out of the building down there, and it's in the process of being fueled and getting ready for our December mission. So enough about me. I'll give you what I got here is our kind of an overview about Orion, and I'll just step through it. It's got a couple of videos. It's got a video up front that gives you a highlight of what the program's about, and then it goes through our charts that give you a brief status. And just one thing to set the stage, and you'll see it in the video as well. I mean, this is a really exciting program for me. We're setting up the capability to take humans to deep space again. And NASA's structured and has really restructured, since the shuttle program's retired, our focus, Orion's focus, is deep space. So missions that start, I say, with the moon, right? Anything that's a deep space location, asteroid retrieval, Mars eventually, those are our destinations. Space station continues to operate. Cargo is carried up and down by our international partners as well as our commercial partners today, and our commercial partners are also trying and working hard to get established as an alternate to carry astronauts back and forth to space station. So that's continuing on. We really kind of work in parallel, and there's some places where we actually have the same hardware vendors, and so we trade information back and forth as it's applicable. But so I've because you hear a lot of discussion today in the media about what's going on with the space station and all the stuff that's going on politically with the Russians. We continue to operate as partners anyway, but my specific mission isn't so focused on space station as it is, let's go back to deep space. With that, let me go next page.
Are you ready to do the video?
Yes. And we're
Okay, so how this is going to work is I'm going to place the URL into a browser. And so on your computer, your default browser is going to open, and it'll have the video in it, and it's going to play on your computer via YouTube. And so we're going to give you about 3 minutes or so. It's a 2.5-minute video. Give you about 3 minutes to watch that, and then once you have seen it, if you can indicate that you are through watching the video by giving us a green check mark. That'll let us know when the majority of you are, make sure you're not having any issues or trouble. If you are having trouble, you can use the chat window. Those chats will go straight to the moderators and we'll try and troubleshoot for you. So we're going to go ahead and try and do that right now. You're live.
Okay, I'm live. For those of you that were looking, that was, we were playing hand puppets. I keep promising people that I work with that I'm going to grow up and mature someday, but this is a fun place to work, actually. So that was the video of the animation of the mission that will fly in a few years. That's what we call exploration. You'll see our schedule and our timeline in a second. What I was talking about a little bit beforehand, right? This is the graphic that we use to talk about deep space. And you see where the space station orbits at 220 miles. Then our missions start with the moon, and then Lagrange points or potential asteroids, and eventually Mars. One of the things I really like about the Orion vehicle and the way we're building it is it's very flexible. We've got a lot of capability. A lot of what we're doing that leading up to our test flight this December carries over to any one of these missions and destinations. Currently, most of the discussion that you hear is about an asteroid retrieval, and so the agency would build a different vehicle that would go out and retrieve the asteroid and bring it back and park it in a near-Earth orbit. And then we would use Orion to go out and be the base of the vehicle to go do human exploration of that asteroid. So that's what's on the books today. We can go to the moon, we can go to Mars. You have to build different parts of of what I call the architecture around it. The Orion capsule and the service module are the core vehicles that the astronauts would use for launch and for entry. And much of your command and control of the mission. But for a Mars mission, it is, depending on when you launch, you're talking 9 months ish to get out there. And so you'll carry a habitation module of some kind. If you think of like some of the lab modules we fly on space station today, something of that scale would also be included in your mission to give the crew more living profile. But, so let me keep going so I don't talk too long on the charts and you can get to Q&A. This is another shot. When we fly deep space, we need a vehicle with the size that you see here. This is the Space Launch System sitting underneath us. For anybody that's seen the Apollo rockets or familiar with it or been here in Houston and seen the one, or in Huntsville and seen the ones there at the Space Center, this is on the scale of those Apollo boosters. We looked there are numbers of ways to do deep space exploration. Do you do multiple small launches and have a space station that you jump off from, or do you end up building a larger infrastructure like this and basing your approach off of this? And a number of years ago, this is the approach that the agency chose. There's a fair amount of commonality in the launch system. If you see the center tank there, that's got some heritage in the external tank from the space shuttle program, and the boosters on the side also have their heritage from the solid rocket boosters that were used back in the shuttle program. Let me go to the next page. There it goes. And so that gives you a scale size. What you saw on the previous page was the stack that you see there on the right that we use for EM1 and 2. On the left is the configuration that we're going to fly here on the first week of December. And so the Orion, the capsule there in the center, the launch abort system just above it, service module below, all sitting on top of the Delta IV Heavy stack. The Delta IV Heavy has enough throw capability that it'll get us out and meets our mission profiles. It was ready, it was available, on this by combining our vehicle with the Delta IV, we're able to get an earlier test flight than we would have and test out a number of our Orion systems. So let me keep going, see what's next. We just updated the charts yesterday, so some of this is a surprise to me. I usually know what's in front of me. Mission timeline, December 2014. Actually, we are working to a December 4th launch date. For people in Florida, they'll have viewing like you used to have on the shuttle program. For folks around the country, and I don't have the exact locations handy in front of me today, but there's a number of museums and other locations around the country that are going to have viewing parties. So if you're interested, last I recall the mission is going to be an early morning launch. It's got a couple-hour launch window, but we'll target an early morning launch and invite any of you that can to take some time and go watch us fly. Next mission, EM1, which is one in the video, is slated for 2017. We've got what we call Ascent Abort 2, slated for 2018. That's going to be another test of the abort system and how the vehicle reacts and behaves when it's exposed to abort vibrations and abort loads. One of those systems we hope we never have to use with crew on board. And I've got a video, I think, if it loaded, of the Pad Abort 1 test. And if the video doesn't come up, I can at least talk about it, but we already did it back in 2010. And then our first human mission right now is 2021, and that's EM2. So let's go to the next page and see where we're at. So a little more about the Orion vehicle itself, launch abort system on top, crew module, which is where I spend most of my time working, and the service module below. Launch abort system is an impressive vehicle. It's a solid rocket motor. If you see the you see 3 of the 4 nozzles there in the middle of it. This thing is used only if there's an emergency on the launch pad or early in first stage ascent. And if the onboard computers sense that the rocket underneath is going unstable for some reason, it initiates an automated command, and that the solid motor in there fires off and it basically carries it and the crew module, separates on some pyrotechnic bolts and carries it away from the stack. The crew sees about 12 to 14 G's of acceleration when it happens, and it's a completely automated command. It pulls it up and away from the vehicle, spins it around, separates, and then the parachutes are able to deploy and the crew lands safely, in a sense like a normal landing. They'll splash down just off the coast of Florida in a case like that. And then service module underneath, you see it says ESA service module. For EFT1 here in December, we built all of it here in the States, starting with EM1, and for EM1 and 2, we've partnered up with the Europeans, and they're going to provide a good portion of the service module. Some of the structure we're building, but there was a partnership that we've developed through our years at Space Station, and there's an agreement made that we would partner up, and so we'll get we'll get portions of the hardware that will be built over in Europe, brought to the States. Final assembly and testing will be done here in the States, and then we'll fly. And that sets the stage for them and us to decide if we're going to stay in a partnership for the long term. Right now, the partnership with ESA is really just for the first few missions. There's enough time for that to develop to let us decide jointly if we're going to continue to do that, if it's in everybody's best interest. Next page. Next page is just a quick comparison of Orion versus Apollo. We look similar. We are larger. It was a crew of 3. We are a crew of 4. Back years ago, when we did have a space station requirement, we could be sized for a crew of 6. So you can put 6 people inside. We're no longer actively working that. So you see a crew of 4. We're slightly larger in diameter and heavier. You see the launch abort system, that light gray shaded was the launch abort system that Apollo had. Ours provides the same kind of function. The shapes that you see coming around the top of the vehicle, the ogive panels as we call them, were added into the design because it makes the launch more efficient, lowers the acoustic noise that the crew module is exposed to by basically reshaping and deflecting the pressure wave that comes off of the nose of the LAS, and that way it doesn't hit the top of the vehicle, it hits those panels. Service module underneath. The crew module when it lands, again, one of my jobs is parachutes and landing. So when we land, we weigh about 20,000 pounds, just as a point of reference. Liftoff weight, landing weight vary depending on consumables that you've used up, what parts you've jettisoned off, what you haven't. So just to give you a rough idea, the crew module alone weighs 20,000 pounds. From a shape perspective, you know, and we'll get comments like, you guys are just redoing Apollo. The shape is consistent. Physics haven't changed. For the reentry to the atmosphere, this shape and what we call the cone angle, which is the angles that you see coming up the side, make a difference. We actually avoided a lot of expense in wind tunnel work and aero heating work by maintaining, even though we got a larger vehicle, maintaining that same, roughly the same cone angle, and that allows us to, you know, to kind of take advantage of some of that Apollo heritage we have. Inside the vehicle is much more advanced, of course. The avionics, or the control panel, is a derivative of what flies in the 787 today. It's been upgraded and hardened to live with our environments, but we have very few physical switches, a lot of touch switches, soft switches as we call them, and you know, otherwise very modernized. Have the same shape, but that's just a byproduct of physics and what the vehicle needs to do. So next page, what's the next one here? So that's just a quick pictorial of a mission that will fly in December. It's really 2 orbits of the Earth. We'll launch out of the Cape, and coming out of the first orbit after we've come around, the kick motor will fire and take us up to a 3,600 mile high apogee. That gets us a very good hot reentry. If you're familiar with shuttle, shuttle's reentry speed was started at around 17,000 miles an hour. 17.5, I think it is. A deep space return is in the range of 24,000 miles an hour. By shaping an orbit like this, we'll get the capsule to 20,000 and a peak heating or a highest temperature in the range of 4,000 degrees Fahrenheit, which is about 80 or 85% of the heating and energy that we'll see on a deep space return. So this gives us a great test of the heat shield and the rest of the tile system and the other systems as well, which is really an important aspect. You can create a 4,000 degree temperature on a heat shield here in the States, but you can do it at what we call an arc jet, one of our test facilities, and those test articles are the size of a hockey puck. It's important to test the vehicle at an entire system level and see how that heating distributes across the vehicle and how the vehicle as a whole reacts, and not rely only on lab testing in a case like this. And so that'd be one of our key test objectives to when we get the vehicle back, is to understand how the heat shield works. We've got 1,200 sensors on the vehicle. 209 of them are embedded into the heat shield itself. So we'll get a lot of data on this mission. So let's keep going. And let's go again. So we're spread across the country. We got, of course, here in Houston, the various centers across the state. My parachutes that I work on come out of California. The mortars that deploy my parachutes come out of Seattle, up there in Washington State. The bulk of our primary structure is welded together at the Michoud facility down in New Orleans. And it kind of varies. I know our avionics and computers come out of Arizona. The industrial complex that supports aerospace and defense is pretty distributed, and so you end up reaching across a lot of different places in the country to find the hardware that you need, at least down at the component level. Right, the major assembly work is done in Florida. Missions control and management of the program is done here out of Houston, but we've got vendors all over the country. We just recently had to put some tape on the heat shield. I think it shows up in a picture. It actually came out of a small company that's up near Minnesota, it turns out. Just as another one of my little factoids. So let's see, next page. So this is an old before and after picture. As you saw last week, we just on the right-hand part of the frame, that's the crew module. Crew modules and service modules that we're going to fly in December. That picture was about 4 or 5 days ago. The vehicle is ready to go. That's in what we call the FAST cell, Final Assembly and System Test. That building has been used since the Mercury and Apollo programs, and so the picture on the left is one of the Apollo modules being pulled out of the same exact test cell numbers of years ago. And the engineers found the photo, and if you look real close, somebody went and positioned a couple of engineers just for fun to do a quick photo and position them in the same general locations. So there's a lot of heritage in that building. So it's pretty exciting to have gotten to spend 9 months and be involved in building the next craft that's going to take humans to space. So next page. And it's just another shot of it as it was being prepared. The tile that you see are a derivative or have their heritage in the tiles that we used on the space shuttle program. You'll see the heat shield in a moment. We use an ablative heat shield on the bottom of the vehicle, on the higher heating areas. On the upper surfaces that we call the back shell, we use what we call Tuffy tile. And those were tile that were used similar to the tile that were used during the space shuttle program at the end of the program. And they give us a really good solution. And shuttle program used to install those tiles basically in place. We've actually got a series of 9 different panels that are assembled off on the side, and then those panels are individually assembled onto the vehicle. So that's a view of the crew module sitting on top of the service module just before we put it on over onto the crawler. Next page. That's the view underneath. This is actually, sequencing, this one's a little bit out of order. This one is, as the crew module was finished before those back shell panels were installed, it was being lowered into the fast cell. And so you see up in the top, you see that green isogrid structure. I don't know if you can get the pointer up there correct. So that's the pressure vessel underneath it. The pressure vessel is really what keeps the astronauts safe. That's how you maintain the atmosphere and the living environment for them. You see a variety of different components around the side of the vehicle. Those back shell panels get installed over top of that. And then underneath you see the heat shield. And the heat shield is the ablator that's called Avcoat. It turns out that's the same ablative material that Apollo used. Early in my career here, we did a number of tests. We looked at Avcoat, we looked at tile solutions, we looked at Pico, we looked at a variety of options and traded and tested and compared them against each other and settled on Avcoat. Avcoat's not shiny silver. It is, what you see there is that silver tape that I mentioned. One of the things we want to do on orbit is keep the vehicle as warm as you can, basically for thermal management, energy management. Adding a layer of tape to the outside of the heat shield helps kind of slow down that heat conduction process. And so this tape will burn off very early in the entry process. It just makes, I think it makes for a cool picture, actually. So next page. So that's a view of the launch abort system. You can see on the picture you see over there on the left that one engineer just ahead of where it gets the cone section comes up, gives you a sense for the size of that vehicle. And so it's been ready. The vehicle's moved out of the ONC. It's being fueled. In fact, we loaded one of the 2 ammonia tanks last night. We'll get into hydrazine loading next week, if I remember right, on schedule. And then we'll move over to the building that the LAS is sitting in, and then stack the LAS on top of the crew module and service module, and then we'll be ready to roll out to the pad and go get stacked on top of the Delta IV Heavy. So next page. Now, are any of these videos loaded?
They are like 75% there. We may have to circle back.
Okay. So yeah, let's go back and come back, because particularly the one in the lower right, all of the shows the pad abort 1 test that we ran back in 2010 and shows how the launch abort system works. So let's go move on and we'll come back to it if the videos get loaded. This was an in-process shot of the service module when it was being assembled. This picture is a couple months old. Let's go on another page or two. All right. Is this video? Okay, so there's a video. Actually, you can find this video on YouTube. Go back a page, if you can. All right, so go back a page, and you see the shape of the vehicle where you've got the top of it, and then it kind of dips in and angles back out. That's the structure of the vehicle. We install what we call fairings. And the fairings are, in our case, are actually part of the load path. You install fairings on a vehicle to help manage the loads that internal components see on ascent. For EM1, there'd be sort of solar panels installed here, and you don't want to take solar panels and install them to the buffeting that you get going uphill, and so you install fairings to protect all these other components from that energy, and it allows you to be a more mass-efficient launch option. So if you go to the next page, and we won't run the video, one of the things we will do on EFT1, and that we've done twice in our facility up in Sunnyvale, was demonstrate that these fairings separate properly. So if the fairings have to come off, if the fairings don't separate, you can't get your things like your solar arrays out, your radiators deployed, and you have to shorten or abort your mission. And so this was a ground test, and the brownish looking skin there are the fairings. There's 3 of them, and they're installed with a series of bolts, and there's a pyrotechnic charge that runs the length of both sides and the top. And there's a hinge at the bottom, and you issue a command, and the pyrotechnics explode, fracture the bolt pattern, and there's a set of springs at the top that push it off of the vehicle. And it just pushes off the vehicle and falls away. So we'll demonstrate that on EFT1. We were doing an early test in the lab, and the first of these 2 tests, when we separated it, and that video I don't have for you, 2 of the 3 panels separated. Turned out that the corners, and I'm playing with my fingers, I'm not sure if people can see that online very well, but the edges of 2 of the panels flexed, and one caught the other and caught it just so that one panel separated and the other panel fell back in place and didn't separate. So we learned that through that test program. Analytically, we didn't think that was going to happen. We got surprised in the test, got informed in the test, which was a good thing. One of the engineers actually came down to Florida and took our flight panels and trimmed the corners to eliminate that interference issue. And then we ran a subsequent test and demonstrated a good separation. Yeah, and it wasn't with scissors, but it was, you should have seen her over on the side there. And so this is just a video of the second test, and so that'd be one of our key ascent tests, is to have good fairing separation. All right, so next page. That's some pictures of the launch vehicle. It's been built. It's down at the Cape, ready to go. We basically buy our ride. When we contracted with the United Launch Alliance for Delta IV Heavy, we're one of their many customers, and so it's been very good for us and for them, and so this will be a good mission for everybody involved. They launch other satellites, other vehicles into space. This is our first, pretty sure, at least on the human side of the thing, maybe on other NASA programs we have, at least here out of JSC and out of the MAN program. It's the first time we've launched anything on a Delta IV Heavy. So next page. Picture of our parachutes. When I'm working parachutes, as you can understand, have to work. We're designed to be fault tolerant, so these are our 3 main parachutes. They each one of them is 116 feet in diameter. So you got a 20,000-pound vehicle that started its entry to Earth at 25,000 miles an hour. You've come down and slid down through the atmosphere, and our initial parachute deployment is at around 300 to 350 miles an hour. That's with our forward bay cover and our drogue parachutes. By the time we get on what we call on final inflation on the mains, our touchdown speed is 25 feet per second. So 18 miles an hour is roughly what we land at. They're designed to be fault tolerant, so if one of those 3 chutes doesn't inflate for some reason, the vehicle still safely lands on 2. The structure and the rest of the vehicle designed around protecting for that failure case. We do most of our, as it says across the bottom, at Yuma Proving Ground. We need a nice it's good to have a large test range to do these tests on. We're actually pretty consistent whenever we touch down and land. But if you have something go wrong in the test, and that's why you're testing, you know, you don't want to be doing this in the back of somebody's neighborhood. Put a 20,000-pound test capsule on top of, you know, somebody's garage. It's really bad form. So it's a lot of fun. It's we've done a Google Hangout. So from time to time we're out on social media when we're doing these tests, just to let folks observe and watch in real time. Next page. Another video that's embedded in here, the forward bay cover, and let's see, the white piece in the bottom of the view. That cone-shaped section has tile installed on it. Its purpose is to protect the top of the vehicle. That's right. My parachutes, my mortars, other radio antenna, and other beacons are recovery beacons are located under there. The job of the forward bay cover is to protect all of that hardware from the on-orbit environment and from re-entry heating, and then jettison off and get out of the way. And it weighs about 800 pounds. This was a test we did up in a lab where we were simulating with those cables and ropes that you see up on top the load that the parachutes put on it. We inflate a set of parachutes for a second and a half, and then we fire a set of small thrusters to basically kick this thing off the top of the vehicle. And the netting was up there because we built one test asset and wanted to reuse it for three different tests. And so we figured out a way, the engineers in Denver figured out a way to blow it off the top and capture it and not damage it so we could reuse it. And so we did those tests in the lab, and then we did a subsequent pair of tests out in Yuma where we jettisoned it off the top of our test article. No, it is not necessarily reused. We will do our best to retrieve it after EFT1 and learn what we can. Just because it's always good to get all your test hardware back because it informs you. You can see things from a distance, but you learn a lot more by looking at it up close. So the next page. So this is a shot of a couple of our astronauts that support us. This is the layout, one of our mock-ups, one of our fairly low-fidelity mock-ups here in Johnson Space Center. If you see that silver structure across the top of the two of them, that's kind of a rough mock-up of the control panel. So it's very compact. A whole lot less hardware is dedicated to flying the vehicle now. And you don't see them in the picture here. The other two astronauts would be, you see the silver panels there over on the right. That's where they would be laying, and they're basically they'd be looking up at the ankles of the other two. So that would be your launch and your landing configuration. And so you're laying on your back when you're launching and entering. You're in that position. So you're going uphill on your back like that. So next page. Mission control. You know, just like in during space station and shuttle program, actually as far back all of our programs, you know, we'll continue doing control here out of Houston, out of MCC, and they've been upgrading their facilities and following all the work we've been doing and getting ready to support and fly the mission. So next page. And we've actually partnered with the Navy. When we recover, the plan is the Navy will use what they call a well-deck ship that you see there in the background. The stern gate is lowered. They send the recovery folks out in those Zodiac boats, line up the astronauts and the vehicle and tow it back into the well-deck ship. And they just finished one of their test programs yesterday. Actually, the first time we did it, we and the Navy got a surprise. About 3 or 4 months ago, the first time they ran it, it turned out that the waves were actually kind of amplifying in the deck of the well deck, in the deck of the ship itself, which surprised us, surprised the Navy. And we learned out of that test, and we've modified our procedure. Typically, when the Navy's putting things in and out of that big well deck ship, they're actually much larger than our capsule. And they're powered, and so it was as big as our vehicle is. When you put it in the back of the ship, it wasn't it was being affected by the waves and moving around more than the recovery forces were anticipating. So they went back out and modified some procedures, and right now off the coast of San Diego, last week and this week, running a series of tests and refining that process. Keep going. So this was the last page. I've always liked this one. This was a shot from one of our outreach events, and you know, STEM is part of is a key part of what we do. I've talked with a lot of groups. I'm always fascinated and amazed by the number of folks that are interested in this. I got to admit, it's a lot of fun. You know, I've always my argument is we should explore and really reach out and find out what we think we know, go understand it for sure, and go find those unknown unknowns. And great countries explore, and that's what we do, and that's what we should continue to do, and then inspire some little guys along the way like that. Is that video loaded? You want to go back to the video?
One video ready.
All right. Show me, or scroll back and.
I'm not sure which. It's just. I'm sure the beginning of it.
Okay. All right. So that one was one of the ground tests of the big abort motor. So that's just it was out at the motor vendor. When they get them downloaded, and I know they're out on other sources on YouTube, that you'll see you got that motor fires, and then there are two other smaller motors that fire out and steer the lass around. And then that the video that was on that video screen page, it was in the lower right, is the abort test sequence that we flew back in 2010. They're really fairly interesting to watch. And work on, for that matter. I know that they're available. This is all public stuff. These set of charts have these videos embedded in them, and the players weren't letting it just letting it roll through. So I'm sure we can link them and make sure everybody has them. So why don't I stop for a minute? You want to go Q&A since it's already 9:45. I still see them. Do I need to go back to hand puppets?
All right, so we are going to do our Q&A with Stu. So what you're going to do is you're going to raise your hand if you have a question. You'll go ahead and type it in the chat window, but you will not hit enter until your name is called. All right, so go ahead and raise your hand if you have a question. Okay, the chat box has now been turned on, so you can now type your question into the chat window. We'll go ahead with Greg, if you want to go ahead and enter, Greg. Okay, you talked about the parachute system on Orion is extremely complex that accounts for many different failure scenarios. How does your team approach testing all of those failure systems when the number of physical launches drops of the capsule is so limited?
Hey, great question. We had that debate with our management team as well. It's a series of things. We look at what are the most likely failure modes, like what would cause a main parachute not to inflate, what would cause a drogue parachute not to deploy and inflate properly. And so we really go through with the experts and look at, all right, what are the most likely scenarios, and use that to sort of define the number of tests that we know we want to run. So it's It's picking the most likely ones. It's also a combination of doing enough testing. And this has been one of the things that I've had to argue and convince our management about. To what we fly, make sure we have enough tests to have a number of demands. If you've seen any of our videos, right, you're throwing these large diameter chutes, giant bed sheets out into the wind. How do we know that they will work repeatably and in that dynamic condition? And so we did a series of individual single chute tests. We actually did about 20 tests of 1 and 2 chute tests, fairly simplified, and then we're doing a series of 17 tests of the whole vehicle. Some have 3 chutes at landing, some have 2, but like the one picture there. So at a full system level, we've settled on 17. Then we'll actually do another 8 or 9 for our final call. I'll give you a sense of how many we actually settled on. Some of it's engineering judgment, and then some of it is, actual looking at taking probability assessments and looking at what the PRA math tells us is a more likely failure case, and using that as a guide for the number of tests. As a point of reference, Apollo did something on the order of 100, a little more than 100 parachute tests of their capsule system. So our engineers think that our 25 or 30 is or 40 is just barely enough. So that's one of those debates because they're a fairly expensive test program. But that's really a good question. Appreciate it. And so and the other thing I will say is we do enough tests that at the end of the day, the experts that do our computational fluid dynamics can model the behavior of the parachutes, because we know we can't test every condition. And so we do enough tests and pair up with our aerodynamic experts to make sure that they're modeling and predicting chute behavior properly. And that's where we end up settling.
All right, Lily, go ahead and hit enter. I have heard that much of Orion is reusable. How much of it actually is?
Most of the internal components are reusable. I'll say in general, all the internal avionics will be reused. Early in our program, we looked at making the entire capsule reusable. Actually, went away from that. We might move back to that someday. When we were going to reuse it, we needed to be able to control how we landed with more accuracy than we have today. You wanted to be able to make it reusable and not force you to do a lot of inspections. You had to land very softly. And that system was, in fact, I was working on it back years ago, was going to require us to carry about an extra 1,500 pounds to make the landing that much more controllable and that much gentler. And so we ended up choosing not to do that. So we don't reuse the structure right now. We don't intend to reuse any of the heat shield or the thermal protection system. For one thing, like you have to inspect, and then you also get heavier. If you're going to reuse the hardware, you've got to design it for multiple uses, and that's mass to orbit. And we try really hard to minimize mass to orbit, given the kind of missions that we're flying. But so internal components, seats, the expensive computers, that type of equipment, we will reuse.
All right, Corey, go ahead and hit enter. As a mechanical engineer, do you find that you are more hands-on with the construction of the spacecraft you worked on, or do you spend more time at the design desk?
In general, because I started, gosh, tell you how old I am, I started on Mylar drawings. So I'm nowhere near that hands-on anymore. I do more of an engineering management function, so most of my life is at a desk. I just finished 9 months down in Florida and got to be very hands-on with the vehicle. Now, in general, all of our flight hardware and the installation and testing of an actual piece of flight hardware is done by certified technicians. And so I would assist in a few cases, but being what they call a project office engineer guy, most of them, like, nope, don't touch the hardware, sir. You're not allowed. So as I've come up through my career, I don't get to do a lot of hands-on work now. Our engineers, like the guys that work on the parachutes, are very hands-on, and their test program is very hands-on. So it's an interesting career thing to figure out what you prefer, or maybe what you're better at, and that's one of the benefits about NASA. I'll do a quick NASA plug. There's a lot of variety on the different styles of engineering you can do depending on where you end up in the program. But most of my day is now at the desk. Sometimes debating with our budget guys that I need more money for parachute testing. And every once in a while I actually go off and dust off and start reviewing drawings and do what I call real engineering.
All right, Walter, go ahead. What's the lifetime of the Orion program?
Let's see. And I may have to ask you to define lifetime. I started working on it in 2006. As you see, we started roughly in the 2010 time frame building the vehicle that we're going to fly here in 2014. So our schedule is to fly again, and we fly humans in 2021. There's no end date per se at this point in time. So it's I assume, and being an engineer, not being in the political arena, that what we call Orion today will evolve into something else in the future. I think we're building an architecture and a capability that even if it's not always called Orion, there'll be aspects of it. It may be called Orion for a long, long time. If things shift and for some reason it's not, a lot of what we're doing will carry over. But so it started in around 2006, and as of today, we're doing budget projections out through 2025.
All right, Michoud, go ahead. What kinds of cosmic radiation are you expecting to find in deep space? And what kinds of measures are being worked on to protect the astronauts from exposure?
That's a really good question. And I'll admit I'm not totally up on that one. I do know, for example, when we fly EFT-1, we'll go out and back through the Van Allen radiation belts. And so we'll get a really good data set on how the vehicle reacts to the radiation seen in the Van Allen belts. And there's actually we did a competition. There's a student experiment, radiation experiment being flown on EFT-1 to give us data that it actually gets fed into the human aspect of it. And radiation protection for individuals is one of the long-term challenges that the agency's got to work on. Theoretically, you could wrap the vehicle in water. You could take your cooling system, and if you think about it, wrap the vehicle in water, and does a really good job of protecting you from radiation. It's also very heavy, right? You can line parts of the vehicle and the living compartments with lead. Lead's really heavy. You got to launch all of that. And so I know this is where I'll say I'm a little weak. I don't know enough detail about what we're looking at that is a good solution that that gives crew really good protection and is I'll say a mass effective solution. As in my program, we're not working on that directly at the moment. We'll incorporate it when it comes online, but other parts of the agency are working on that one.
Okay, Edward. What is the most challenging part of your job?
Let's see. I don't know. Gosh, that's hard. Half the time, I think it's turning off when I get home. It's an interesting thing. You get so engaged in this, particularly when you're doing something where you're putting humans into space. It becomes very personal. It takes time to step aside and not worry about it at night and cut yourself off. Probably maybe second to that, I would like to go faster. I like what we're doing. I would like it to be happening faster. For it to happen faster, we need to convince our stakeholders, being, you know, Congress and the White House, and the rest of the country, for that matter, that we need to bump up our budget. You know, you got to balance us against everything else going on in the country. So the schedule that we're on today fits the budget profile that we're on today. But I get frustrated because I like to fly as opposed to practice flying, and so. Dealing with that is probably the other challenging part. The technical stuff kind of comes and goes. The technical challenges are the fun part. You know, there are days when the technical challenges make you bang your head on the wall, but that's what you signed up for too. So that's why we're doing this.
All right, Kate, go ahead. Have the Mars rover missions helped to develop or further advancement of the Orion mission?
I don't know if in many direct cases they have, although I can tell you in our parachute world, one of the engineers that's on our team, or a couple of them, were actually involved in the Mars rover missions, and so some of our deployment, some of our ways of testing, and some of the lessons that they learned from that mission, just by the fact that we've engaged them on our team, has been part of it. There's probably in the communication and avionics world probably more lessons out of that than that we've incorporated that I happen to be aware of. You know, that's by comparison a very small robotic vehicle. And so, one of the good things that NASA does, although I would say a lot of times it's done sort of ad hoc and formally, is that these engineering communities aren't all that large. The engineers that did the guidance on the rover know the engineers that do guidance for us, and like I said, they share information back and forth. They share their lessons learned, the challenges, and the oh craps that they came across, and so that happens almost. I mean, it just is a normal part of the job. People will share data back and forth. Specific ones, I don't know that I like. Outside of my experience with the chutes, I'm not sure how many other exact lessons learned that came out of that one. All
right, Stu, well, we're coming to the end of our session, and the videos are downloaded now. Would you like to go show those?
Go to the PA1. Go to the PA1 video. The one was in the lower corner. And while you're setting it up, I assume I'm still live. Again, this simulated a pad abort. The computer thinks something's going wrong on the launch pad. It's time to get the crew out of harm's way. And you'll see the vehicle lift off. It gets about a mile in altitude in 2, 3, 4 seconds. It's hitting about 500 miles an hour. When it starts to pirouette around, you'll see the launch abort system separate from the vehicle. The little jets up on the nose of it is actually how it steers. It separates, and then we go through the parachute sequence. And so let that video run. So go to before we have to get off you have to hang up. Go to the very last chart, because I forgot. There was, after the picture of the kids, there was one more page. And yeah, that's all of our links. So I would, if you guys aren't already following us, that's the links to our various social media sites. Hook up with us, pop us questions. I think our Facebook page is. I know we can do a good job of keeping it current and updating it based on all the different tests and events we're doing. And most of the videos that you have are somewhere buried on our Facebook page. And so we like thanks for all the questions. I don't know what you want. If we got more questions, I've got the time. If we got to cut off, I can keep going unless we're going to turn into a pumpkin or something. So keep going if you want to.
I don't think we'll turn into a pumpkin.
Okay.
All right. So Scott, go ahead. You work on parachutes and recovery systems, and Orion is going to Mars. Are you involved with the landing systems to be utilized on a future Mars mission?
Not today, I'm not. I might get to in the future. Like I said, that community's small enough. Gosh, when we were looking at land landing, we were looking at a variety of combinations of like crushable honeycomb, deployable legs, thrusters, those types of things. And so when the funding gets serious and we get serious about landing systems on a Mars lander, the group of us that work that kind of stuff will probably get engaged at some level. But so right now I'm not. I've keep myself pretty busy just working on Orion at the moment. Actually, I hope so. That would be a lot of fun.
All right, Jason, go ahead.
All right.
If the Orion program were given triple the current budget, what types of additional equipment or sensors might be added onto the Orion?
Let's see, triple. Wow. See, that's good. Although you should ask for 4X. I want. Don't stop at triple. If you're going to write your congressman, we would add. Let's see. Probably an extra test flight or two would be my one of my first thoughts. We'd accelerate the work on the lander, like we just talked about, right? And we'd accelerate work on habitation module that would be worked in the architecture. On Orion itself, one of the challenges we've had, one of the things we've done to keep our costs down is, since we're not putting astronauts in it until 2021, is we actually haven't spent a lot of money working on the upgraded seats and EVA suits, the life support system. Right? We've got the systems we need to run the avionics and computers. We haven't spent a lot of money yet on the human aspects of the vehicle. And so within Orion itself, we put money against that. I know I got 2 or 3 more parachute tests that I'd like to run. But I think if triple would be fabulous. A lot of it would go to other aspects of the program over and above what Orion's doing. Like when you mentioned sensors, we've got 1,200 sensors on the vehicle that will fly in December. We'll have right now our budget plans for 800 on the EM1 mission. There's some we'd bump that number up if we could. You always get into trades on how much weight you add. Anytime you add a sensor, you add the wires that come with it. That adds weight. Do you have to have that be a flight sensor, or could you get that on the ground as well? And so we always do that trade. But triple would open that discussion up, and that'd be a lot of fun.
All right, Greg, go ahead.
I think we'd end up going and getting some of the
From your bio, you have a BS degree in engineering. However, most job descriptions in space technology today look for MS in engineering. Could you give us your perspective on the educational requirements for jobs in the industry?
Yeah, I work with a lot of folks with advanced degrees. At the time I got out of school, I would say the BS got me into an entry-level job, and that combined with work experience turned out to be sufficient. And that's probably, and that maybe that varies. I don't know across the whole industry anymore. If a master's or an advanced degree is required. I do know that, like when we hire here at the center, a bachelor's is a must. Advanced degree is good. Work experience and interning and co-ops is probably, I would say, more advantageous than an advanced degree, just from the folks that I've been exposed to and that have done the hiring. The agency has a really good co-op and intern program. A lot of industries do that as well. I think looking back on my education, I came out of school, I went straight through in 4 years, not because I was that smart, but probably because I wasn't smart enough to do something different. I got out and I was very good, broadly educated, but when they sat me down at a drawing desk, I was not really a very good draftsman. And working on a CAD machine, I had one class in that in school, and so from that aspect, I didn't have enough really good work experience, which was a challenge for me at first. Yeah, I would push a little bit of work experience over an advanced degree. Maybe it depends on the kind of work you want to get into, right? If you're all the folks that I work with are the CFD experts and the guidance and nav experts, the ones that I think are really, really smart, the vast majority of them do have an advanced degree along the way somewhere.
What does an average day in the engineering life as a student consist of? What challenges do you face?
Let's see. I can tell you that, so it varies, but since we've been getting ready to fly the vehicle, I'm usually in by 7, and I'm gone by 5. Although when I was down in Florida, I was running 10 to 11 hours a day routinely. And again, some of that is because you get so wrapped up into it, and if you enjoy it, the time goes by. The agency's always kind of is juggling, like a lot of agencies are, how many engineers, how many people do you have working here? And so we're trying hard to balance. You don't want to have a big bloated staff, always having the right skill mix. That said, a lot of, like my day is every morning at 7:45 I'm on the phone with the guys at Kennedy Space Center to see if there's anything that came up in the vehicle testing overnight that I need to be working on. And so that'll sort of set the stage for the day. As we transition from EFT1 to building to EM1, it shifts to preparing for design reviews or reviewing the next procurement spec. It's sometimes the day-to-day challenge is looking down the to-do list and prioritizing which one needs to be done today versus which one can I wait till tomorrow, or which one can I wait till Saturday and have quiet time to read that report.
Okay, James, go ahead. Could you go into more detail on the Orion habitation module? What would that vehicle entail?
Well, it hadn't been designed yet. My expectation is that if you think of, like I said earlier, a module like the habitation modules that we have up on Space Station today, something and so those were the scale of 40 or 50 feet long and 20, 30 feet in diameter, something like that. So you've got a big system like that. It would have your life support systems into it. It would have your crew habitation, galley, all of that worked in, radiation shielding you have to deal with. I would actually expect that for a really long duration flight, we would take the crew module and actually have it kind of power down and go quiescent. They're all attached. You'd have the hatches open, and the different modules would be attached to each other. And you'd, in a sense, be able to fly your mission from that habitation module. Beyond that, I would say, take a good look at the next time they're doing ISS Live and get an idea of what the inside of their living quarters looks like. Today, I think that would be, given today's hardware and technology, probably is what it's going to continue to look like. Beyond that, I'm kind of guessing, so I probably should stop guessing.
All right, our last question from Edward. Go ahead, Edward. How do you tackle difficult technical problems? What is the mindset you go into? What is the mindset you go into to break a problem down? Well, for example, we just had a problem, and I was down in Florida about 3 or 4 weeks ago. One of the things that you do after landing is you upright the vehicle. And we have what we call uprighting bags, and they're
pressurized by helium bottles, 6,000 psi helium bottles. One of a series of them developed a leak, and we realized that to maintain the vehicle schedule that we had about a week to implement a fix. And so sometimes your mindset on the problem is a function of, in our case, the schedule that we had. It will drive us to, you have to actually gather your facts. Personally, I like to sit back for at least a little brief moment in time and get a lay of the land, right? Take a look. All right, here's what's out there. Here are my major constraints. What has to be fixed? What might be fixed? What's sacred versus what's not sacred, and use that as a guide. Start with that. One of the tools we use is what we call a fishbone, right? If you don't really understand the problem yet, you make a fishbone diagram. You say, all right, I've got a leaky tank. That's the end of the fishbone, and then you start drawing bones of your fish to say what could be causing that. And so you systematically go through what are all your potential failure drivers, and then you look back at the other data that you have in front of you and start to eliminate ones that are not potentials, and then start focusing on the ones that do. But actually, one of the things that helps me is because it is very easy to get caught up in the, oh my gosh, we got a problem, everybody goes running to the fire, and kind of pause for a moment and take 30 minutes of quiet time and sit back and go, okay, let's think about this, and then go straight. But that's just my personal style. Okay. So that was my last question. All right. Let's see. Tell me how this is going to work. So you got to hold this. Can you see these? That's the logo. That's the sticker for the mission, and same thing in lapel pin form. And then that's our little patch, Orion logo patch, until I'm not really good at this camera stuff, am I? I'm an engineer, I'm not a social media guy. Let's see, so I'm told that if you complete your assignment, although I must submit a final project, okay, complete your final projects, that you get stickers, and I'm sure my cohorts have all your mailing addresses. But, so, there's goodies out there. I've bribed congressmen with stickers. Well, not bribe. That might be a little strong.
We'll cut that out of the recording.
Thank you. Take that out of the recording. But stickers, you always get stickers. So, but appreciate all your interest. Appreciate your interest in the program and all your questions. And like I said, follow us if you can. Come watch us fly in December. Anything else?
I'll come up there.
Okay. I'm getting kicked out of the chair here in a minute.
My life on the chair.
All right. Well, we want to thank Stu for joining us this morning. And that was a great presentation, and I'm sure you learned a lot of information on how you can plan your mission to Mars, your robotic mission to Mars. I just wanted to send out a few reminders. Make sure that you're trying to attend your instructor's office hours. They have them going on all this week, and you can ask them questions about your final project. The final project is due on September 24th, which is a week from Wednesday. So if you have questions, please email us, and we are looking forward to seeing all your great presentations. And I'd like to thank Stu for doing a great job today. So let's give him a round of applause. Virtual round of applause, everyone. Do you guys remember how to do that? Yay! Where is it? There it is. All right. So see you next time.